All right, we've got everybody back. Hello, everyone, and welcome. My name is Liz Stein, and I'm a systems engineer and partner here at Prime Movers Lab. I'd like to start by welcoming our audience, all of our limited partners, our founders, and especially the new LPs who are part of the Growth Fund. And for anyone who's new to us, Prime Movers is a deep tech venture firm, and we specialize in investing in scientific breakthroughs that have the potential to positively impact billions of lives. So our topic for today, and that is orbital debris and the impact to the space environment. But before we get started, I'd like to plug our next webinar on October 27th at the same time for brain rejuvenation. So real quick housekeeping as well before we get started. We'll keep this strictly to an hour. We'll have some questions ready to go for the discussion, but there's also the ability to submit questions live through our Q&A feature, and please comment in the chat. With that, I'll turn it over to my most excellent partner, VP of Engineering, Christie Iacomini.
Hi, thank you, Liz. Yeah, I'm Christie Iacomini, VP of Engineering at Prime Movers Lab. I'm really anxious to dive into our topic today on orbital debris. Spacecraft launches per year have increased tenfold in the last decade, and the trend is not slowing. In fact, we're going to see it increase fivefold in the next decade. Satellite demand is being driven by the growth of all these mega constellations that we're seeing being brought to us by SpaceX, Amazon, OneWeb. And this is to provide relatively inexpensive global telecommunication services. Meanwhile, the behemoth communication satellites and geostationary orbits are not going away. And to add to that, in the neighborhood, there's uncontrolled whole defunct satellites that maybe were unable to complete their mission for whatever reason, and relic spent stages of launch vehicles from the last several decades. Then literally pepper the expanse with shards of debris that have maybe been created from fuel tanks that have exploded with residual fuel, thermally cycled batteries, or even in-space collisions of some of these things as well. And these smaller pieces are just now whizzing around, intersecting orbits, and causing a pretty big problem. So these objects can literally take out our space assets. And when they do, then they can create even more space debris. So the threat is growing, and it is a significant threat as life on Earth depends upon this infrastructure that we're building in space for services like telecommunications, national security and defense, global navigation, we use it every day, all of us, weather and climate change monitoring. So how bad is it? And what are we doing about it? I'm really, really thankful to have this stellar panel with us who are experts in this field and are already doing something about it today. So with that, let me introduce you to them and have them tell you a little bit about themselves. We'll start out with Dr. Moriba. He's an associate professor at the University of Texas in Austin in the Aerospace and Engineering and Engineering Mechanics Department. I went to UT, so I'm excited about that. He holds the Mrs. Pearlie Dashiell Henderson Centennial Fellowship in Engineering. So Moriba, tell us a little bit more about yourself, please.
Yeah, no, thank you very much. Thanks to everybody. So here at UT Austin, I lead a transdisciplinary research program in space safety, security, and sustainability, which hopefully will unpack a little bit more of what that means during this. My background is astrodynamics, science that studies motion of stuff in space. After doing Mars missions at JPL for about 7 years, I went to work for the Air Force Research Laboratory. That's when I became acquainted with stuff orbiting the Earth and the amount of junk and stuff that we have. And then in a moment of weakness, I left the government for academia to pursue this kind of research stuff. So I coined myself a space environmentalist and really looking again at linking things that we've done, land, air, sea, and now space.
That's fantastic. Thank you. Next, I want to introduce Carolyn Belle. She's the Director of Advanced Systems at Astroscale US. Carolyn, tell us about yourself a bit.
Thanks, Christy. I'm happy to be here today. So I work at Astroscale US. We are a company looking to enable satellite servicing as a means to drive towards space sustainability. And so excited to be here today to talk about debris, which is one really critical element of that. My background has been in commercial space. I got my entree to the field in astrobiology at NASA and realized quite quickly I was so passionate about this vision I held in my mind of what the space industry could be, what services we could provide from space to life on Earth, and how do we get there. So I followed a path of the enabling services to make that a reality. And for me, space sustainability is a critical level that we need to reach to be able to make that happen. So that's why I came to Astroscale, and that's why I'm happy to be part of the conversation.
That's fantastic. Sharing passions with all of us, I think. Austin Link is not the last and well, anyway, whatever they say. Austin Link, you're next. He's the co-founder of Starfish Space and also a local resident here in Seattle with me. So excited to have you as well. Please tell us about yourself.
Great to be here, Christie and Liz. Thank you for putting together the panel. Excited to be a part of it. I and Starfish Space generally are a little bit newer entrants to the problem of orbital debris here. Some of my background up until almost 2 years ago, I was at Blue Origin. So Christie and I actually worked together a little bit there. And then in leaving Blue with my co-founder, Trevor, we started Starfish Space, where we're developing satellite servicing technologies. And one of the missions for our Otter space tug is to help dispose of satellites at the end of life, to manage debris, maybe mitigate some of the potential for collisions in the future. We're still an early stage company, but maybe to give a sense of the scale, we're based in the Seattle area here, and we recently announced a $7 million funding round to help grow and move towards really tackling this problem.
Well, congratulations, Austin. That's great news. We're excited to have you here as well as the others. So let's get into it. We already started to talk a little bit about the problem, what's been creating the problem. I want to dive into that a little bit more. How is this debris created? What is the space environment like? How bad is it? What's real big? What's real small? I'll ask Moriba to set us up for this conversation. So thoughts?
Yeah, look, really we're looking at things, right, ranging in size from like speck of paint to the space station, but we can't measure the entire population. So we can't form a census of the entire population. We can just measure some samples. And one of the things that I tell people is, if you want to know something, you have to measure it. So the measurable stuff maybe goes down to like cell phone size kind of thing. And like you said, I mean, we have things in different kind of orbital highways, and we don't just uniformly populate space, right? We have this nice orbital highway called Geosynchronous region. And the thing is, you know, if we have to find ways to fight gravity to achieve the same stuff, that's a losing proposition. And so, you know, too much wasting of fuel and that sort of thing. So the orbital highways, they're becoming more congested. Most of the stuff that we put up there doesn't come back kind of thing. And when things die, they don't just naturally decay, so to speak, but they keep on going at very fast speeds. So, and the highways intersect with each other, and there are no stoplights. So that's really everything from nuts and bolts, right, all the way to pieces of solar panel. And when satellites age, they fall apart. Space object gerontology, as I call it. And yeah, and then working satellites, once they die, they're also hazards to everything else.
So you point out the different sizes, the small versus the large. I'm curious, is there worse debris, or is there a debris we should be focusing on first? For example, I've been reading like somebody made a top 50 list of the big items that really are probably most critical to take down first, or would you disagree with that hypothesis?
Yeah, so that sounds like my brother Darren McKnight, who's now at Leo Labs, who's with his top 50 thing. He's quick with his top 50 list, right? That sounds like what was it, like the top radio charts or whatever, the top 50 things to get out, right? Back in the day. So yeah, I think that here's what I honestly think. I think that we need to be and people and not or people. Like I feel a lot of people are saying, oh, do we remove the rocket bodies or do we remove, it's like, no, we need to be and people. And in fact, when people say, hey, what kind of debris removal technology is like the best out there? It's like, it depends on what you want to take out. Like there is no Lord of the Rings, one technology to rule them all kind of stuff. Different technologies serve different kind of purposes and different sizes. And so I think that for sure, the top 50 in terms of derelict rocket bodies, those have to be brought down because they're ticking time bombs. And we already have evidence of explosions in geotransfer orbits that are now horrible. So that's those are what I call super spreader events. Okay, they definitely make the COVID, the equivalent COVID thing in space kind of spike up. But then you have these sun synchronous orbits, right, that are quite busy. Maybe you don't have all these rocket bodies necessarily at sun sync, but whatever debris exists there, there's already evidence that these old Russian satellites and other stuff are actually impacting objects as well. So we kind of have to say, what are the most, what are things that are going to be super spreader events, and where do we have most trafficked areas to where we need to start removing some of that congestion from those orbits?
Yeah, so real quick, so you mentioned geosynchronous, sun synchronous, and you haven't talked much about LEO, but that last point makes me think about LEO, especially with the mega constellations. So maybe take just a brief moment and tell our listeners real quickly what those three things are: geo, sun synchronous.
Yeah, so I'll say, kind of in layman's terms, we're talking everything from like the Kármán line, 100 kilometers to about 1,200 kilometer altitude is low Earth orbit. Geo is at about 36,000 kilometer altitude, plus or minus, say, 1,000 kilometers. And then whatever isn't in between those is called mid-Earth orbit. So that's kind of the general way that people have classified things. I don't like it, but it is what we've called it. So.
Okay, but that's good terminology, so everybody understands. Thank you.
Christie, if I can just hop in on that comment about being and people, and I think this goes into a lot of what else we'll talk about in the session today. But when you talk about very small pieces of debris, such as those we can't track today, but are still potentially threatening depending on what orbit they're in, versus the large pieces, it's what is the timeline of the feasibility about removing those, right? I think there's broad agreement that all of them do present threats, but looking at where are they, what are the other satellites that are operating there, what is the technology that you would use to remove that specific class of debris, and then what is the business case for doing that? Who pays for it? What is the policy and the regulatory side around it? So there are a lot of different pieces that are distinct depending on which type of debris you're talking about. And so that's why we do need to look at them as not exactly the same thing, not the same problem.
Moriba.
Yeah, I mean, yeah, I raised my hand just because I want to do something really quick here. And just trust me, Card, I want to share my screen real quick because I think this will make a lot of sense. Can I do that?
Yes.
All right. So here we go. So this is something that we put together not too long ago. And basically it's 4,000, a snapshot of 4,000 objects, human-made anthropogenic objects. And so this is in like 3D Cartesian Euclidean space kind of stuff. So here you can kind of see this geo, this outer ring is like geo, just to put things in a context. Mid-Earth orbit stuff are some of these like cyan things. And then low Earth orbit is all this stuff in the middle. Now, the color coding for all these dots, each object, is the inclination. How inclined is their orbit with respect to the Earth's equator? So things that are close to like orbiting in the Earth's equator are 0 degrees inclination. Things going over the pole would be like 90 degrees. The interesting thing, and the reason I show this, is because we've taken all these 4,000 objects and I'm going to be a little bit nerdy here. We computed their specific orbital angular momentum, basically cross product of position and velocity. And this is what you get. I didn't do any clustering. This is now this angular momentum space. And you can see how these objects naturally fall into these highways. I didn't do anything except do that simple math. And it's the same 4,000 objects. And you can see the magnitude of this angular momentum says something about the orbital energy. So geo things are here in this halo on top. Mid-Earth orbit stuff is here, kind of in the middle here. And then you can see all the low Earth orbit stuff at the bottom. And then you can see here, these things are basically sun synchronous here at the bottom. So it's very interesting to map these things into this orbital angular momentum space. So you could like literally and figuratively see these highways, and it's not uniformly populated. So.
Wow, that is super helpful.
That map is fantastic. It actually leads me into our next series of questions, which is how we're tracking space debris. So Moriba or Carolyn, if either of you wants to kick off that conversation, in terms of, are we tracking from the ground, from space, a mix, right? How are we doing space situational awareness today, and how should we be doing it in the future?
I'm going to let somebody else speak for a little bit because I don't want to hog the whole thing. So.
Okay, I can hop in on that. And then please, you can correct me, Moriba. I think that would be the best way to go about it. So Right now, we're doing most of our tracking from surface of the Earth, right? So we can do both optical or radar-based tracking. Each of those have different advantages in terms of, what is the smallest piece of debris that one can detect, and exactly where is it, how much you can characterize it. We are getting towards doing more space-based tracking, and certainly there are satellites in orbit today that are doing space-based tracking. And there are proposals that are in place by various startups to enhance that so that we have a broader data set of space-based data that can complement what we detect from the ground. Right now, with SSA, there's no global one solution for it. We have the U.S. Air Force that provides space situation awareness, so tracking, and provides potential collision warnings to satellite operators. They, send out these conjunction data messages when there's a potential collision that's arising, but then nothing else happens, right? The alert is sent out, and it's up to the operator to figure out how it is they want to respond. We also have private companies who are providing space situational awareness data, and some of that is using publicly available data. Some of it is using their own data based off radars that they have built. Companies like Leo Labs has built a series of radars around the world to be able to enhance the number and the size of objects that we can track. So there are more solutions coming, but again, there's no one cohesive way for operators to ingest that data, decide how or if they want to respond to that potential collision, and then connect with the other object, whether that is a satellite that is in operation by another operator, whether it is a piece of debris. So again, there's some lack of overall management globally for that.
Agreed. And then if I can jump in with a follow-up before hearing Moriba's opinion, my follow-up question would be, if there's going to be a conjunction of two commercial providers, who moves? Like, are we playing chicken in space? Who pays for the fuel for that move? All right. Yeah.
I mean, I think any of us can jump in on that. Right now, there's no hard and fast rule about who moves. Sometimes it's a logical choice because only one of them has the ability to move. Say you have two active spacecraft and only one of them has a propulsion system, then it's easier to think about that person or that operator moving. But there's no hard and fast rule. There's no requirement. So it's up to them to coordinate. We have solutions such as Slingshot Aerospace just released a new platform the last month or two that would provide a direct communication line for those two operators to assess how it is that they wanted to respond, and would assess, okay, we think it's advantageous for you to move in this situation because of propagating out where your satellite will be and future potential conjunctions. But no, there's no requirement today.
Yeah, I think So first of all, Carolyn, I don't have anything to correct you on for the tracking. Spot on, tickety boo, awesome. And yeah, I think that, before getting into this whole coordination thing, Liz, about who moves, I think there's an underlying assumption that, and I don't mean to necessarily point to you in saying this, but I think a lot of people think that that basically a conjunction or a collision notification like that is the case. And what I'm telling you is that it's not a given that there actually is a collision risk. And so part of that is because probability of collision, which is what most people use, is very subjective. It's a very subjective thing. And so it depends on the data that you have. And so maybe Leo Labs with their radars, they have their own hypothesis about some collision, but that may be completely different than, say, the US Department of Defense with their own sensors, because they come up with stuff with their own data, which is different than what ExoAnalytics is going to come up with and that sort of thing. So one of the things that I tell people is, how do you know that you have the world's most accurate clock? And the answer is you have hundreds of them. And this is the reason why it's important to aggregate these opinions about collisions, because nobody has the truth sensor that's going to tell you for sure that something is going to collide. These are all hypotheses or beliefs based on their own data. And the thing is, there's no kind of aggregate opinion about when things may or may not collide. So people actually have disagreement about collision probability type stuff. And basically what it really says is collision probability probably never should be used as the only basis for deciding when you should or shouldn't move in space. And I'll say that another thing that I propose in terms of trying to reconcile or adjudicate who might move out of the way is if people are very transparent with where their satellites are and where they're going to be, almost like filing a flight plan, right? It's saying, listen, for the next week, I'm going to be on this path, plus or minus 100 meters. So this is where I'm at. And if people do that, then it's my opinion that if somebody else, right, is going to be in the way, they should probably have to be the ones that move out of the way, because somebody took the responsibility of filing their flight plan and telling everybody else where they're going to be over some interval. But that's just, nobody's asking me, right? So that's just my opinion.
I like that though, because you think about it in terms of almost like a localized space real estate then, right? In order to launch something up, you have to get that initial permission, right? You go and you file at the ITU, right? So by filing a flight plan, similarly, you're saying this is my local real estate that I'm inhabiting and so on.
But here's the care. The local real estate is basically time varying, meaning, and the reason why I say that is because I've already heard, and I think that this is complete and utter stupidity. I can't believe that some people like, oh, well, I have this orbit, so nobody else can be up here. It's like, are you kidding? Like, that doesn't make sense. Like, they want to have
an entire orbital plane. Wow.
Yeah. And that doesn't make sense, right? It's like, if I have a plane that takes off from Austin to San Francisco, it's going to be on one of these air vectors. It's not like no other plane can be on that air vector until that thing lands in San Francisco. Like, that's not how we do air traffic. So why should orbital traffic be similar? So I think the real estate needs to be centered on the object, but it needs to move with the object for some interval.
Yeah, agreed. Austin, I see you were able to jump back on. Do you have any comments or thoughts on traffic management before we move to the next topic?
I am able to jump back on at least here. Can you hear me, Liz? Just to check. We moved into a new office like a week and a half ago, and clearly not all the Wi-Fi challenges are sorted out yet. I'm not sure that I have a ton of value to add in terms of space traffic management, but it's an important part of trying to address the problem, because even though we work on the back end on how do we dispose of dead or defunct satellites that are potentially causing debris and aren't mobile, for ones that are mobile, for ones that are dodged collisions, that's oftentimes a more affordable way to do it while your satellite's functioning. So that's a great approach, and to be able to sort that out better, and I think, like Moriba mentions, be able to actually scale to tens of thousands of satellites being in orbit, which is what we're going to see over the course of this decade, is important to make sure that while we are managing traffic, we're not just doing it with the broad, this is your orbital plane, that's your orbital plane, and never the two shall interact.
I will point out that, Austin, you're the one who pointed us to yesterday's breaking news about Privateer and how they are looking to make the Google Maps of space. And so when you think about having that capability, hey, I know exactly where I'm at. I don't know if you guys want to give an opinion on, does that help our problem here?
Yeah, so I mean, that's one of the purposes of Astrograph, right? Is to be able to serve that purpose of being something like a Waze for space, basically a participatory sensing network that basically ingests data from users, and the same group that can input data can also make use of it and have an aggregated opinion on where is there, up on the side of the road, be careful, there's a hazard, this, that, or the other, right? Something that could be used almost like a near real-time, space traffic map. And so I'm fully on board. I'm biased, fully on board with this idea for Privateer to do that.
That's great. All right.
Just to add on that, Christie, I was going to say it's also helpful in the planning phase of assessing risk and which orbits might potentially have more objects in them than others. If you have some flexibility in where you can put your satellite to achieve the mission, it's helpful for that.
and as a space debris removal company looking to where to park their assets to be of service to others.
Indeed.
That would be good too. All right, so we've talked about what is orbital debris, what does it look like, where does it live? We talked about how we track it, how we keep track of it, and maybe some things that are coming that'll allow us to track it better. Let's move into how do we take care of it. So we've been talking about Liz and I have been talking about there's two different ways to do that. One is through remediation, clean it up, remove what's there, and the other one's through mitigation. So we want to explore those just a little bit. We're going to first dive into remediation. Let's take care of the problem that exists right now, and wanted to explore your thoughts on that. What are the current techniques, if we could say there are current techniques? What do you think technologies are interesting for remediation? Maybe somebody'd like to tell us what remediation even means. Austin, you want to kick us off in that area?
Yeah.
Now that you're back.
Now that I'm back, so hopefully I'm not repeating what other folks smarter than me have said here. But I'll say is you sort of frame it there, remediation as we have this debris, what can we do about it? And at the moment, there's not a whole lot that we can do about objects that are in orbit that you might want to remove from that orbit. Now, when you're in low Earth orbit and really the lower ranges of Earth orbit, when you're in the few hundred kilometers that are closest to Earth's surface, then a lot of times the atmosphere over time will cause orbits to decay and eventually re-enter and burn up. And so some debris in those realms naturally gets remediated. There are also some technologies, things like here in Seattle, Tethers Unlimited has their Terminator tape that is a way for smaller assets to maybe enhance their deorbit by generating a little extra drag, potentially even interaction with magnetic fields there. I think that what we're working on at Starfish, what Carolyn and Astroscale are working on, other folks too, is, well, how can we clean up some of the larger objects that are potentially problematic? And in some ways, these larger objects have potential to be more problematic than smaller objects. One, they just have a larger cross section. There's more potential points to intersect with them. But also the larger objects can, when things go wrong, become many smaller objects, right? You can either, if for some reason you have a battery issue or a propellant issue and have an internal source of failure or deconstruction there, but also if you're a large satellite and you collide with another large satellite, you create thousands of pieces of debris. And we saw this with an Iridium satellite in 2009, I think, that led to thousands of objects in the orbit. And so one of the things that we focus on, say, with our Otter Space Tug is how do we grab these objects and then drag them into low Earth orbit or into a parking orbit that isn't as useful to folks and isn't as crowded, a graveyard orbit type. And there are again a variety of objects for which that is possible or isn't possible, but we think it opens up the opportunity to remediate some of the larger objects in orbit that are potentially more problematic.
How about technologies to do that remediation?
So when we're developing the Otter, it in effect, it's a satellite that has the ability to grab and move other satellites. And so if you have a satellite sitting in a 1,000-kilometer altitude orbit, and for some reason you go, okay, this is end of life, we need to dispose of it, it's not capable of doing it themselves, because that's the first pass that you might do for remediation. You might burn your own engines and dispose of yourself. And something like our Otter Space Tug serves as a backup that can attach itself to the satellite and fire our engines to drop you off in a lower orbit where you'll naturally quickly decay and no longer be a hazardous piece of debris threatening the infrastructure that we're building up there.
To jump on that technology piece about what distinguishes remediation from this next topic that you said we'll get to, Christie, of mitigation, right? So remediation with Greece already there. One of the biggest challenges we face with that from a technology perspective is that none of those objects were launched with to be prepared is what we call it, with servicing in mind, right? They weren't launched with the idea that sometime in the future they would be grabbed by a robotic spacecraft and removed from orbit. The other thing is that for many of them, they're no longer controlled, so they might be tumbling. So that means that instead of moving along in a very orderly fashion throughout their orbit, they might be moving and sort of tumbling and rotating consistently. So when you want to send up a servicer to go up and dock with one of these, it's complicated because you have to be able to match the tumble rate of the servicer with the client. And then you have to have a docking solution that can grab onto something that wasn't designed for it. And you have to be able to safely move it after you grab onto it. So you have to grab it at a structurally sound location. So these three things sort of add up to drive what is the solution that we develop, and how do we implement it safely so that we don't create more debris, because that's the effort that all of us are undertaking in servicing. Number one, don't create more debris while we're trying to solve the problem.
That's a great framing. Go ahead, Moriba.
Well, so the thing that I'm going to say, right? So yes to everything that's been said. I think that there's an elephant in the room, or the 600-pound gorilla, or whatever, the very heavy set large animal that nobody's talking about. And to me, it's this. People really focus on the tracking of the objects. And the thing is, when you focus on the tracking of the stuff, most people, and in fact, the largest single database. So with Astrograph, what we've done, right, is we've been aggregating everybody's opinion, including the DoD. But the DoD is like the biggest donator of stuff related to information, that's stuff on orbit. But even that database models every single object like it was a cannonball. It's a sphere. And to the points of both Austin and Carolyn, you're not rendezvousing with spheres. Okay. You're rendezvousing with things that have different sizes, shapes, material properties. In fact, anything that's not being actively controlled is tumbling. So that's most of the stuff up there. And there's no database that we have where we can actually see and understand all these physical characteristics of the object: size, shape, tumble rate, material properties. There's actually science that needs to be done to make that close, so that when we go look up an object, it's not just where's this dot located, but where's this dot that's tumbling at this rate and made out of these things that could satisfy these technologies for removal. None of that exists on the right now, and for the foreseeable future, that's not going to exist either. So a lot of the business models of folks that are on this panel with me require some knowledge about this sort of stuff. And it's like, where are they going to get that from, right? There's, again, no place right now to look that up. And if we just wait for governments to do that, I got bad news for you, right? There's the whole bunch of paint that is drying, and that it looks a lot more exciting than waiting for the governments to do this sort of thing. So I think we need to be proactive as a community. We need to generate this database of a trait-based classification scheme of all these anthropogenic space objects. And when we have that classification scheme of the CubeSats, the rocket bodies, the blah, 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 and oh, by the way, here's what they're made out of and that sort of thing, then we're going to be able to say, okay, this technology that Astroscale has is really optimum to do remediation for these things. This stuff that Starfish is doing is really optimal to do remediation or to do, tugging of these things. But there is no place, there's no digital commons to look that up now. And it's very frustrating to me because I hear the conversation stopping at the tracking, but not the classifying the objects in terms of their physical properties. And we have no a priori information on this stuff. So that's the hard work. Nobody wants to do that hard work. And that's really frustrating.
No, that's great.
So how we're, not getting around that challenge, but trying to move through that for our first mission is that it's going to be a two-phase mission. So the first phase of it, the first spacecraft that we launch, so this is our Address J mission in 23, is just to inspect an upper stage. We're not even going to try and remove it because we need to have that understanding of, it has been in space for more than a decade now. How has it changed in that time, right? How has it degraded? Fully characterize it so that then we can more safely plan for the next phase, which will actually be to remove it. Now, is it going to be economically feasible to do that for every piece of debris? no, which is why, like to Moriba's point, we need to have this resource that everyone can lean on.
All right, can I add something to that? Because I really want to. Pretty pleased with sugar on top.
There you go.
Okay, so here's the thing. I'm going to lower my hand just because I want to be a gentleman that way. And I want to show something really awesome to you folks, and I think you're going to like this. And so one of the things that I'm trying to motivate, right, is being able to do as much of this inspection on the ground as possible. Like if we don't have to launch something to inspect, if we can do it from the ground with current sensors, that's cool. Not that you shouldn't go inspect on orbit, do that and inspect from the ground. So one of the things that we've been looking at is, so here we go. So here's a model of TOPEX. TOPEX is a dead satellite in about 800 kilometer altitude orbit. It's tumbling. This is a CAD model of TOPEX. So we kind of know what the thing looks like. It's fairly well characterized by satellite laser ranging people. And so the dots that you see, we actually developed a photon counting device. So this thing counts photons, individual photons reflected off of TOPEX at 50,000 times a second. And what you see here, every dot is some number of photons that we counted from TOPEX. And so what we can get from the ground are all these dots. The redder dots are more reflective surfaces. The greener stuff is more diffuse reflection. So what we'd like to do is this science. We'd like to collect these dots, these photons, count them from the ground, and then say, okay, we actually know how to interpret these to then reconstruct what the 3D model actually looks like. So given this collection of dots, generate the thing that actually looks like TOPEX. That's the inverse problem that we want to solve. But again, I'm looking for my Medici equivalent. It's like we're in the Renaissance. The Medici family funded Leonardo and a bunch of other people. I'm like, where's my Medici equivalent so that I can like get an army of people to really accelerate this sort of technology? And so far, it's crickets.
All right.
Do you mind if I follow that one up before we hop on to the mitigation topic then?
Yeah, you go, Liz.
Okay. So, I think that's really interesting, your question about like, who are the kind of philanthropic folks who are interested in solving this problem, right? Is this something that just the classification alone is its own business case, or should it be an open access database and maybe everyone can contribute their information to it? So I'll leave that hanging in the air in case anyone has any.
Well, so here's the thing, right? There's something called citizenscience.gov. Basically, it only requires somebody within the US government to be the point of contact for this. I promise I'll do everything else and I'll make it open science. I'll bring in everybody's data. I just need one person in the US government to just say, I will be your contact and we can do this as under citizenscience.gov. The website says all the steps you need to do to like make this sort of project happen. Nothing. It's just, so yes, I believe that there's merit in the crowdsourcing, the citizen science. I think a lot of good could come from it. We just need somebody who's not afraid to say yes from inside the government.
Would you be interested more in a civilian person like NASA, being the point of contact there, or a DoD? Do you have a preference? I know folks at both, and I would like to help.
I don't have a preference, really. In fact, 99% of all the funding of my research comes from the DoD. So yeah, the DoD cares about this clearly, right? The problems happen is when, all of a sudden it's like this overclassification of stuff, and maybe there's stuff we don't. So the DoD has reasons to do that. So when it comes from a civil entity, there's a lot more relaxed kind of feelings about these sorts of things.
Yeah, we'll get to that in a bit because we want to touch on dual use as well. But let's move into mitigation. We're going to start running out of time if we're not careful.
Okay.
Can I eat into running out of time a little bit here?
Go on.
For jumping in, but I do want to emphasize that as we think about these problems, we talked there about the philanthropic side, the government funding side, can you have your Medici family of today to help make this happen? We also maybe clearly think that there are aspects of this that aren't philanthropic, that aren't government funded, that are just a good business case. And when you are when debris is threatening this infrastructure at the core of $1 trillion economy, then that debris is causing people's problems, and removing those problems is potentially a good business. And that's why we founded Starfish Space as a company to solve this problem. And I think that one thing that we need to loop in on the technology side as we think about what are the technologies we need to do this, one of the key technical problems to solve is how do you do this affordably? Because if you're going to make a business case out of it, if you're going to make it so that it's really worth disposing of dead satellite here or unresponsive object in the constellation there, the value trade there depends not just on what are the value you're getting out of it, but what's the cost that it requires to do that. And I'll say that's another side of the technical problem that we try to solve is, well, how do you do this really efficiently so that way it's worth solving the problem, and in particular for us, we're solving the problem as a company to do so.
So I have some thoughts on what makes that monetizable really quick. And to me, what makes that monetizable is if we can agree to sustainability metrics like orbital carrying capacity, like a space traffic footprint that's a carbon footprint analog. As soon as we can say, this is the carrying capacity of this orbit and it's being taken up, 99% of the capacity is being taken up by these dead things that are owned by these 3 countries. Now we have a basis to go and poke and say, hey, sounds like you need to remove this stuff because you're taking up capacity, or you get this much money for providing this amount of capacity back to this orbit, that sort of stuff. But without the sustainability metrics, we're going to be in this endless cycle of chasing, we're going to be the dog that caught the car. The dog never wins out of that one.
I'll say, I think in part that's true. And then I think there are some new dynamics emerging that makes that not necessarily true for certain types of spacecraft. So for one, a classic problem of orbital debris, this is a tragedy of the commons, right? And everybody feels a little bit of the pain. So who feels enough of the pain to actually pay to solve the problem? And in particular, when you're thinking of that old 1970s Russian upper stage floating through, like nobody feels the pain to remove that. And I don't see a business case for removing that. And I'm not sure Russia would be super excited about me grabbing their stuff on orbit anyways. But one of the things that's notable about the change of the space industry over the last 10 years, and really where we think it's going, is the rise of the mega constellation. The idea that you might put 100 or 1,000 or 10,000 satellites in one orbit. And that has made it so that the tragedy of the commons is no longer as much of an issue. When you have a dead satellite, when you leave a satellite in your 1,000 satellite orbit, the person who feels basically all of that pain is you. And so when you want to keep your constellation operating, because you need to, this is the infrastructure at the heart of your business, then it becomes worth it for you to pay to dispose of your satellite so that it's not a danger to you. And this is something that is not just me saying it necessarily here. We've seen this in our conversations with commercial satellite companies. I'm sure Carolyn has seen the same thing in her conversations with commercial satellite companies. And so I think there are paths to us as having our services being paid for that don't even necessarily require on the international coordination, that they don't require the international regulations that maybe have been traditionally viewed as necessary to build a business case around this problem.
Yeah, so you think about it more in terms of not just being a good neighbor, but in terms of keeping your own work environment clean, like, for FOD and that sort of thing, right? So
yeah, that's a great way to put it, Liz. Your dead satellites become FOD in the middle of your orbit, and next thing you know, your constellation could be falling apart because of the stuff you left up there.
I saw Carolyn came off mute. Do you have a follow-on to that?
I did. Well, just in that it's a different conversation, I think, than the, I think we've now moved into the mitigation, right? We kind of circled around you, Christie and Liz, for we're wanting to shift, but that's where we are now, because this is not getting rid of something that was launched without the idea of being removed. This is working with operators today as they design and build their spacecraft with sustainability in mind, right? Make sure that design, the materials you use, how much of the satellite is going to burn up on reentry, how much redundancy do you put in for its own deorbit solution, and then do you prepare it for servicing in the case that there is some failure in its ability to deorbit itself, right? Whether that is in the prop system, some other system, maybe in the communications link, so that it can be removed from orbit. So, thinking ahead of time and building that stuff in makes it much more cost effective, to Austin's point, that it needs to really make sense from an economic perspective for these mega constellations. And we've seen some of them already buy into that. We have been working with OneWeb and the European Space Agency. So OneWeb is a large mega constellation, and they're taking that step. They're taking the step to prepare their spacecraft for servicing down the line. And it's not just this question of making sure that your satellites are removed from orbit at the end of their design life, or the end of the period in which you're required from a regulatory perspective to bring it down, but also is the extra sort of insurance that you get from having a serviceable spacecraft that can be removed of a benefit, because it means that you're more willing to accept the risk of running your spacecraft beyond the design life, which means you can get more incremental revenue out of that spacecraft. So that's another element that helps them see the value proposition in what Austin and I and others in the industry are talking about.
That's great. That leads me into kind of the next series of questions on mitigation in terms of the regulatory environment, right? There's kind of these guidelines and how long you have your little piece of real estate before you ought to deorbit, right, to be a good neighbor. And there's guidelines on fuel reserves for that decommissioning. But do you think we'll see in the future guidelines on required propulsion to be able to get out of potential collision events and things like that, or requirements for secondary hardware for on-orbit servicing? So I'll open that question up to all three of you and let you guys arm wrestle for it, perhaps.
I've been talking a lot. I have lots to say, but I want to let other people chime in for sure.
Okay, good. I have a hot take question for you after this one as well. So.
Well, I'm excited for the hot take question. That'll be fun. I'll jump in on that. So, this is something that has been talked about for a couple of years, especially the propulsion side of things, requiring propulsion even on CubeSats, right? So satellite that's this large that traditionally has not been built with that in mind. I go the other direction of specific technology requirements, and more of the opinion that if our goal is sustainability of the orbital environment, the ability to continue using it, to continue using these orbital highways, we need to make sure that that's the goal that people are looking towards, not ticking boxes and having specific technologies that are seen as the solution, because that's something that can get in the way of innovation, because maybe there's a solution that hasn't been come up with yet. So it's more encouraging people and writing smart policy and smart regulation in a way that gets us to that sustainable environment with a variety of different possible paths.
I'll echo that's a great point, Carolyn, on orbital debris is a problem and a problem that we need to solve, but so is climate change and so is global connectivity. And as you're putting up these satellite constellations, you're helping solving great problems, and you need to be cautious about putting too many roadblocks in the way for them that are weird boxes that they have to check that are painful to do. And so it's important to be thoughtful as you produce regulations. And then I think we recognize the speed at which the government sometimes moves and the uncertainty with which it moves. And so we're going to learn a lot over the next 10 years about how it unfolds and what are the things that they require or don't require, propose or don't propose.
And great, thank you guys. Now for my spicy question. So there's quite a few different organizations who want to kind of provide a regulatory framework. The UN has a Peaceful Use for Outer Space Committee. There's the ITU. There's an ISO standard for space debris. There's the Interagency Space Debris Coordination Committee. That one's which is like all 13 different space agencies, right? So everybody's kind of working towards this. And I'm one of the things I was wondering is, does somebody come up with something like space debris social security, right? Like a giant pot that when you go file a license or when you want to do anything on orbit, you chip in a little bit towards that so that there's always, some funding there to go and do these operations. And then the different debris removal companies that are out there can bid for the ones that best fit them when that classification information is available. So that's kind of my spicy question, and Moriba, if you wouldn't mind taking a stab at it first.
Yeah, look, I mean, when you said spicy, I thought you were going to come up with something like really provocative or whatever. This is like easy. This is like a lob kind of thing that you did. Look, Outer Space Treaty really holds states responsible for liability, damage, all these things. And I just think that governments need to level up. Governments need to come together and say, look, we have to provide authorization and continuing supervision of all these activities. We're the ones that bear the liability. So just like, right, there's a tow truck company that goes and can remove things from the side of the road, and there's funding that's put to basically have these sorts of services. We, the countries that are making use of space, need to just holistically come together and just agree to some of these practices and protocols, and let's just test it out. Let's not start off with the treaty or the law that says this. Let's just try this out together, like-minded folks, whatever, right? And just try it out to see how far down the road we can get. And if it seems to be something that makes sense and it's working, then we can kind of codify this sort of stuff in treaties. But let's just start it as a practices and protocols kind of thing, just as an experiment. I just think so many problems could get solved if people just agreed to doing an experiment versus it's the all or nothing, right? It's the binary kind of the binomial distribution of we've got nothing or we need to have laws that, you know, are punishable by death and stoning or whatever. It's like, those are the extremes. It doesn't make sense.
Yeah. All right. I'm watching my time. I know, Moriba, you've got to take off.
Yeah, I gotta go soon. That's right.
So let me give you a moment so that if there's anything else you want to share.
Look, I just want to say this. I'm just happy to be here. I'm so happy that you decided to bring one of these academic people on board, kind of stuff. I know crazy stuff that I gotta say, purely academic. But no, it's been great here talking to all of you. Carolyn, Austin, I think that the stuff that you're trying to do is critical. It's needed. So bless your hearts for being here and doing what you're doing. And if there's anything that I can do to help, you know how to reach me, kind of thing.
Awesome. Thank you so much for joining us.
Thank you for your time.
Oh, and by the way, please check out eyesonthesky.org. It's all about storytelling for space environmentalism, and I need people to get enrolled in that. So eyesonthesky.org.
All right. Thank you. So one more, we actually have a question from the audience, as they say, and I wanted to throw that out there before we move to closing remarks for Carolyn and Austin. So let me pull that up. There's actually 3 parts, and I think we've been touching on a couple of them, but the one that we haven't really touched on is if we don't have solutions for removal, is the equivalent of terrestrial landfills, does that make sense? Basically collecting debris in a single place, waiting for recycling technology to catch up. So I don't know if anybody's thoughts about that. I know it's like trash for treasure, right? And somehow, and we also think about the graveyard orbit. Maybe that is our literal space landfills when we're so high up in geostationary that it's not practical to bring them back down and burn them up in the atmosphere, but rather we store them up in this graveyard. Maybe that's our area of potential future recycling.
I'll say, Christie, you just stole my answer. I mean, I think that's basically what that is, the graveyard orbit. And so for folks who don't know, geosynchronous orbit is that orbit altitude is a very particularly valuable orbit to be able to, in effect, hover over the same point on Earth. If you're just a few hundred kilometers out, it's not really that valuable anymore. It's a long way with a lot of communications delay, and you're still moving over Earth's surface. And so when geostationary or geosynchronous satellites retire, they move them out about 300 kilometers to what's called the graveyard orbit. And in fact, there are a few other regions and altitudes that are considered graveyard orbits that aren't useful for very much. And the idea is, okay, we store the trash there. And that is definitely a more energy efficient way to solve the problem, especially when you're as far out as geo. And then I think there is a lot of value on if you put all of the effort to launch these materials into orbit, which is expensive, finding a way to reuse them up there would be tremendous. And how exactly do we reuse them is something that's definitely a technical challenge and not necessarily something that somebody's going to launch in 2022. But it's I think that's a great opportunity for, well, how do you take advantage of some of the materials that you're storing in effect, these orbital landfills?
Carolyn.
Yeah, I mean, I agree with that. There's a lot that we have put on orbit that could potentially be reused if we have the right technology up there. I mean, there are a few things that challenge it. In GEO, it's more straightforward, like both of you have talked about, because we already do have that graveyard. In LEO, the satellites are in much more disparate locations. And so when you talk about the energy that is required to move them to one place or another, yeah, maybe it can be more efficient to move it to a trash dump sort of location, but it might be more efficient to just bring it down and re-enter. So that's going to be something we have to think about. The other thing is, you know, space is not like piracy on the high seas, where if you grab something, it's yours. It still remains the property of the original satellite operator and the responsibility of the launching state that authorized that launch. And so that's something that would have to come into play as well if you talk about recycling. It's getting the right permissions to do that. That being said, I think it's the direction that we're going to go in. I'm really excited about the potential to do that, to be building on orbit. We're based in Colorado. I'm very pro Colorado industry, and we have another great Colorado company that has been formed to address this problem. They are developing foundries in space with the idea that they will use materials that are in space and create feedstock from them and then be able to 3D print something new. So I can send you the details, Christie, if it's helpful, but we're doing an event with them next week to share more about the tech and their progress on it so far.
No, yeah, super interested in that. Yeah, the other thought I had is, you guys are building your vehicles, you're going to go out and you can grab things. I can imagine in 10, 15 years, they go up to these areas and they grab something and they pull off a battery that still is working or some piece of electronics that's still working that they can take then to another customer and help rebuild something. Obviously, to your point, Carolyn, it's not going to happen, or maybe Austin, you made that. It's not going to happen in the next year or two, but that's part of the future of building out all these on-orbit servicing capabilities. So we only have a couple more minutes. Liz and I, again, want to thank you both and give you a moment to have any closing remarks. Sort of the prompt is like, what's next? What should we really be focusing on, or what are you really excited about? Or so Austin, why don't you close us out, and then I'll ask Carolyn.
Yeah, so first thing I'll emphasize is thank you guys for putting this together. Thank you for having me to be up here on screen, at least when my internet's working, with Carolyn from Astroscale and Moriba is an honor and very excited to be here. I'll say that broadly, as we think about the space industry, there's only more and more satellites going up, and that's great because those are going to provide tremendous value. And a decade from now, there's going to be somebody, whether it's Starfish and or Astroscale and or just other folks, who are interacting with satellites on orbit and helping extend their life and helping them take risk and helping dispose of them at the end of life. And what we're going to find out as well, are we going to have a few collisions and have a lot of heavy regulations that are sort of required to get us there? Or are we going to be able to act early on the problem and be able to make it happen? And I'm hopeful that we can act on the problem and make it happen. And I think that, the awesome stuff Astroscale is doing with their LCD mission here, and, we're at an earlier stage, but some of the technology we're working on and flying in space right now is setting a table where we can use this technology to mitigate orbital debris, and also, as we scale, really provide infrastructure for an autonomous future in orbit with a variety of industries and capabilities out there. And to me, that's an incredibly exciting future to even just sit here and talk about, and who knows, maybe we can make it happen.
I'm getting goosebumps. Carolyn.
Yeah, that's the future I want to build towards as well. So I'm really excited that we have people in the industry now who are actively doing that, right? That we have several companies, more than several companies that are moving us in that direction. So, I mean, I would think, as you initially pitched us this idea of closing remarks, Chris, one of your questions was, what is the technology tipping point that we're going to have to face as we move towards addressing the debris challenge? And as I thought about that, I don't think there is one. I don't think that technology is going to be the tipping point. I think we're there. I think we have the capabilities to do it. I mean, we're testing a capability on orbit now, and the technology will follow. For me, it's more a tipping point around our behavior. Those of us who are in the industry, who are designing, building, launching, operating satellites, need to start doing that with a sustainability approach in mind. And even those who are regulating it, I mean, that's a really important piece as well. And I think that is what is going to enable the future Austin just described. Like, are we putting interfaces on satellites so that maybe that battery can be removed and replaced by something else in the future? So I think it's really more internalizing a paradigm shift in how we engage in space. We're not just launching something and abandoning it once it's done working. We are launching something, reusing it, recycling it, repurposing it, and that all starts with how you design that from the beginning.
Yeah, we've done so much. We can learn so much from. So let us be the leaders in enabling that instead of finding ourselves in a situation that then destroys us. Thank you for that. Liz, I think we're done. Do you have any other?
No, just thanks for both of you, and a thanks for Moriba as well. It was so wonderful to hear from you guys, your opinions and thoughts on this. And as an aerospace engineer, I'm really positive for the future with our solutions to space debris. So thank you guys, Carolyn and Austin, for your time. And thank you, Christie, for finding all of our awesome panelists.
Yeah, thank you. And thank you for our listeners for joining us today. It was a great conversation. You guys have a great rest of your week.
Thank you.